All right, welcome to the channel, guys. Hi, welcome. I want to say I appreciate all my loyal subscribers, and if you're new to this channel, welcome to the channel. I feel you guys are like a family. You're following me and stuff, and I appreciate that. Today we're going to talk about a device I employ in a lot of my circuits, and that's going to be the diode. It's a PN device. I got a little picture here to try to show you a little bit about it, because this is the actual diode. This is the actual device right here, and I don't know if you can actually see that. I doubt if you really can. But this device is this is the picture of this actual device. I blew it up so you can see it. Okay, on this on most diodes you have like a ring right here, and that's what this is, so you can see it. This is blowing up a little bit better so you can see it. And that's usually cathode in. That's how you determine your negative side of the device. This is the anode side over here, and this don't have any ring on it at all. It's just, you know, black silicon. And it's your anode device, so it's a positive. And conventional current usually flows from the positive to the negative in that direction. If you try to reverse the voltage or current coming into it, it would get blocked by this device. So it can be used for a lot of purposes. The purpose we're going to talk about today is going to include how we use diodes to rectify. Because actually this is not a signal diode, this is more of a rectifier type of diode. And there are differences. There's a lot of the Zener diodes, there's a whole bunch of different. But today we're just going to focus on diodes that rectify or convert energy to direct current. And I'm going to show you even in a circuit how we actually do that. But for now, I'm just going to talk about how this thing actually works. It has a, you know, in the side of the device, you'll have like a positive region and a negative region. Well, when you electrons are allowed to flow, if you're going in the right direction. If you're not going in the right direction, electrons are not allowed to flow, and that's what makes this like an on and off switch. And in a way, you can think of it like that. But only if the voltage is turned around for some reason or whatever. Give me a second. I'm going to bring up another drawing that's going to show you a little bit more detail. Give me a second. Okay, I'm going to show you in this little drawing I put together for you. One of the purposes, like I mentioned, of the diode or rectified type of diode, you can use it to turn AC into a DC or direct current. Like I mentioned, you know, the diode has two junctions. You got a negative junction, which is your cathode, and you got a positive junction, which is your anode. Well, if you just take a diode by itself, like one diode like this right here, and let's say you have a transformer. This is going to represent a transformer for now. I'm just going to let you see that. If you take a transformer that, you know, it has 120 volts AC coming in and putting out 12 volts. Well, before I get too far with that, I got to mention this particular circuit that I'm going to show you today is not exactly it's a safe circuit, but it's dangerous. And the reason why I'm saying that, because we're going to be dealing with live voltage from your wall or wherever you're going to get your electricity from, mostly from your wall. And 120 volts AC is quite deadly, so you got to be very cautious. If you're not used to working with AC, just watch the video. Don't duplicate what I'm going to show you here. But anyway, I'm going to be taking a transformer like this, which looks like this. And we're going to transfer it from wall line voltage, which is what this is connected to, you know, like where you plug in a wall, okay, to 12 volts output, which is on the secondary. I'm going to explain to you what I mean by that. Set this aside for a minute. Okay, your primary coil, there's two coils in the transformer. There's two in there. That's why you have the two sides. You know, you got a primary here and you got a secondary coil. The primary coil is a bigger coil, and it's used, you know, when you plug it in a wall or any AC, it can handle it. It makes it magnetized. This material here is the core. It's covering the core, actually. And that core lets the magnetism from this coil shoot through the iron core of the metal into what we call our secondary winding, which is going to be here. Secondary winding picks up that magnetism and converts that magnetism into a AC voltage and current of its own. But because it's dependent on the windings. So there are transformers that can convert 120 to 6 volts, 120 to 18 volts, 120 to 12 volts. In this particular device I have here that I'm going to show you today, it converts 120 to 12 volts, which is a safer voltage level to work with if you want to be building something by hand and everything like this, which is what I do most of the time. Well, what you got to know about this is that, if you were to, not use, let me show you, if you were to touch if these caps weren't on here and you were to touch this with your hand, you can get a very nasty shock, okay? Now, if you touch this end of the device, you can still get a shock. Trust me, you can get a shock. You'll feel it, but it won't kill you. This side, the red side, will kill you. The blue side will say, okay, that person don't know, and let you slide, okay? So, what I'm going to tell you is that just be careful when you're playing with live voltages, live line voltages. Now, back to what we were talking about. Rectifiers are used to change this AC output that I told you. It's AC here, but it's AC here at lower voltages. In order for us to use a power supply of any sort, it has to be converted to a DC voltage or DC output. And what I mean by that is anything like you got these little devices that have you plug your phone into it and you plug it right in the wall. Well, the way that works is there's a transformer within here, or something to break down the voltage and transfer it from a high voltage, dangerous voltage, to a safer level voltage for you. And so, in order to do that, you need some sort of rectification. Rectification is just a simply way of saying turning AC to DC. So, I drew this squiggly line you see here is just a representation of what's really coming out of the transformer without any rectification whatsoever. And what I mean by that is that this shows you that the voltage output you get at this terminal is not going to be smooth. It's going to be a ripple. It's going to be a ripple type of wavelength coming out. And that's why you can feel it, because it's going in the direction, in the way it's working, it's going backwards and forth, and it's doing it at a very fast rate. And they put that rate in hertz, what we call hertz, HZ, like HZ, is in hertz. And most people, you have 120 volts coming out your wall, it usually be at usually 50 or 60 hertz, okay? The standard, I think, is 60 hertz, or whatever, so depending on what country you're in, but that's what it is. So the speed at which is changing direction is known as hertz, okay? And so you know that. All right, now let's go back to this. When you introduce a rectifier into the system, into the circuit, or one of these lines, like if I was to attach that end to that end of the transformer, I would rectify only one side of the output. Remember I mentioned there's a signal coming out of here that is rippled, and ripple is simply that. It means it's not coming out in one direction. It's coming out in two directions. It first goes one way, then turns around, go the other way, and it does it at this many cycles per second. So when you rectify it with one diode, you're only going to get half of the signal smoothed out, and the other half is going to have ripples. So it'll be like, let's just cover that end up. You'll still have all those ripples. You have all these ripples here. This side, however, this side over here will be nice and smooth. It'll be nice and smooth. And that itself can be okay for some circuits, but if you want a cleaner signal, you're going to have to somehow rectify both sides of the both directions of this wave that's coming out of your secondary transformer coil. And there is a way to do that, and it would make the signal much cleaner and stuff like that. And the way we do that, we do what we call we make a bridge. A bridge is simply a circuit that consists of 4 of these diodes like this. There's 4 of these guys configured in this type of design. And I put one together to try to illustrate that just a little bit for you. You know, these things here are the same as the diode that is here, okay? Well, you put it in a design like this, where you have your, you know, your cathodes going together, your anodes going together, and then those that have the mismatch ones are where what ties into the output of your transformer. Your AC will enter here and here, and when you to get the DC out, you would get the DC from the ends that have the same poles, like here and here. Those would be DC output, and what that would do, it would change this ripple to a smoother signal like this. It'd be more of a straight line. It won't be going backwards and forth. The backwards and forth will stop at when you get to the bridge. When it gets to the bridge is going to rectify going one direction and rectify going the other direction. So you're going to have a smooth straight line signal. No more ripples going to be involved in that. See, I'm going to show you how that actually works and why you want that. But first, I'm going to tell you, once you got the bridge constructed and everything, when this circuit would no longer be like AC. It'd be DC, kind of like a battery. Like a battery voltage coming out of a battery. This is all DC. I can touch this all day long with my hand. I wouldn't put my tongue on it, but I would touch it all day with my hand, and it won't shock me. And this is almost 4 volts in this cell, but it won't shock me. Okay, and that's DC. That's DC power. So, and that's what you want in a lot of different circuits. Is DC power to power your things like your phone, your laptops, or any else device that uses a battery. I know a lot of people think that when they plug their laptop in the wall, is that their laptop is running on AC. Essentially, it is, and essentially it isn't. What's happening is that inside your computer, it has this setup. Setups are different designs, but it's the same principle. You're going to have the input from the wall, of course, 120 volts, which you plug the little plug into the wall. And your power pack is going to have a transformer in there. And it's going to have a rectification type of circuit in there. Mostly a bridge, because bridges can be made very clean. The signal can be made very clean. And what I mean by clean is that although you have rectified the signal, it can still have some slight ripple in there. And I'm going to show you what you can do to fix that. And these things is called this is a capacitor. And what a capacitor does, you parallel it, like I got here in this little drawing here. You parallel it with the lines. So the negative go to negative, positive go to negative. And what that would do, as this voltage is coming in here and it's got a ripple in it, well, it would just smooth out that ripple even more, making it more cleaner, less noisy, less of a buzzing sound. If you was to hook a speaker to it, you would hear a buzzing sound. But it would be less of that with the introduction of a capacitor, simple component like this. And you want that capacitor to be equal or greater than the voltage that you're supplying. To put something smaller to this would just explode this device. So you want to make sure it's a big enough device that is equal to or greater than the supply voltage you're feeding it, that you're trying to filter. And that's what this is really going to do. Is it's going to filter your signal. Okay. Now, what I want to do next is show you some more solid state type of rectifiers, and you can get a package that looks like this here. I got this wire. I'm gonna show you one without the wires. When you buy it, you can get these on Amazon, and stuff. These are solid state, single package rectifiers. And you have on here, it even got the markings right here. You got AC here, and DC here. So you got AC, and usually you tie the pins in across from each other. AC, DC, DC. So like I got wired here, I got the positive pin of the bridge with the wire on it, and I got the negative pin of the bridge with another color wire on it. And I'm going to show you how this thing actually can rectify a signal from AC to DC. So let's get started with the actual components, and let's put something together. Hang on. Okay, I'm back a little bit here. I'm going to show you a circuit using the AC, the raw AC power output of the transformer, which is on the secondary line, which is, I just tapped it with the multimeter. You know, I tapped it with the multimeter so you can see the voltage on here. I want you to pay attention to the voltage on here. And you will, and also these lines here are going to the motor. This is a DC motor, meaning it only should run on direct current. But what I'm going to show you is that, remember I mentioned how energy, when it's AC, it's going that way, and then turn and go that way, but it's doing it at like about 50 hertz a second. Okay, well, that's what I'm going to demonstrate here. This motor is going to try to turn this way, and it's going to try to turn this way. It's going to be doing it so fast that it won't move. It can't move because the way the motor is set up to run, it needs to run in one or the other direction constantly, not flipping back and forth. So I'm going to plug some energy in. I'm just going to plug it in the wall here into my AC line, which is 120 volts. I'm using a lot of precaution here, trust me. Okay, we're going to give it a demonstration. If you listen really close, you might hear the humming. You hear that humming the motor's doing? When I touch this, it's vibrating. But look at the voltage. It's 13. But look here also. This is AC signal coming out. This motor is trying to turn, but it won't turn. It won't go either way. It just won't work because it needs DC. I'm going to undo the power here for a second. Let that go back down. And what we're going to do this time, we're going to introduce the rectifier circuit I told you about. I'm going to introduce that in there. This line is dead right now, so I'm not worried about touching. That's why I can grab it. And also I got gloves on too, so I'm not going to worry about it. Okay, this is a rectifier circuit like I showed you in my handy dandy diagram like I want to show you. Okay, this circuit here is represented here. I got it in a bridge rectifier configuration. The AC is coming in here. This represents AC. It's coming into the diode here and here. DC coming out of here and here and going to a load, which is our motor. Alright, okay, here we go. Now, I'm going to hook the motor to the DC output of this circuit first before I do anything else. I'm just going to, it don't matter what direction, it's going to only spin in one direction. So I'm just going to put this here and I'm going to go, let me see what the other one is. It is here. Now right now I got this motor, bring it where you can see it. I got this motor tapped at the DC outputs of the rectification of this bridge. You know, these other lines here are the AC inputs. So I'm going to go ahead and put that in there. Put that in there on AC. We're going to do that. And I'm going to show you, as soon as I get this hooked in, trying not to disturb too many things here. Okay. I want to keep my meter connected because I want to show you on the meter that it's still going to be AC. But when you rectify it, you can get something like that, something that works off of DC to function. All right, of course, watch the meter and watch what happens to the motor when I plug the power back in. I'm plugging the power in, so on this side it's going to have 120 volts AC. This side is going to be spitting out 12 volts AC, but it's going to get rectified through this circuit here. So here we go. Power is now on, and as you notice, the motor is able to turn. It can turn in one direction. And if you notice here, you still got an AC signal. The AC signal go all the way up till it meets the bridge. And when it meets the bridge, it gets converted to DC. Now, what I'm going to do, I'm going to actually show you how DC can work, the reason why you want to be able to rectify it. Because if I take the lines from here, take one from here, and I reverse them, with DC, you can reverse the direction of a motor. As you notice, it's going back the other way now. You can only do that with a DC supply. You can't, with AC supply is not, it won't allow you to go backwards or this one direction or back the other direction. It will, you know. So, okay, let me discontinue the power here for a second. All right, now, so that's what the bridge can do. The bridge gives you the ability to run something that works on DC direct current. And one of the advantages of having direct current is the ability to reverse the direction of the power from a negative to positive or positive to negative. You can reverse it and stuff like that. So And that was just one, that was just my rectified circuit I made. I'm going to show you the one that you, if you buy one that's pre-made, I'm going to show you what happens with that. Let me show you. I'll show you a bridge, a different bridge. I'm going to disconnect this one. Power is off, so it's safe that I'm doing this right now. And this is the bridge we talked about earlier. Remember I mentioned that you can buy these bridges. These have a heat sink on them too. That's why that, I mean, they don't have a heat sink. That you can put it to a heat sink. See that little hole down through there? You can bolt this to a metallic surface to dissipate heat. Because this will get warm if you're using a whole lot of current, which I'm not using in this particular device, the project right here. I'm going to go ahead and put the AC lines back onto this bridge, but this is a solid state bridge. So this one is all-in-one package bridge. I got the code number to this bridge, type of bridge also. I'll give it to you in a minute. Right now I'm just going to try to alligator clip these suckers on here and still keep my leads there. Still keep my meter leads on. That's what I'm trying to do. That's why I'm having such a hard time. Okay, that's one. I'm just going to go ahead and connect this one up first before I hook the meter to it. Now, these meter wires are heavy, so it's hard to it's hard to hold them. I'm just going to let it lay on the side, but I'm going to hook the meter back so you can see that it's still AC coming in here, but we are going to have DC output. Now, the DC is going to be coming out of, let me put this back in here, out of these two lines. I got a red one here. This is for positive. I'm just going to hook it to any random line on my motor. And I got the negative here. I'm just going to hook that up right there like that. And I believe everybody's in there. Make sure you can see it all, dog. Want you to think I'm cheating here. All right, there. So this is the wires coming from the DC motor. They're going over to the bridge rectifier, which is the same, which is going to provide the same function as this circuit I built. But except you can buy this in one package if you don't want to build this, because you can actually make this out of 4 individual diodes, you know. Okay, so now we got that together. I'm just going to proof check my everything, make sure nothing is crossed together, make sure these are separated. They are. These are out. And it always pays to check your stuff before you plug up something of this caliber. Alright, so I want to power it up. And if you notice, the motor is going around in one direction, because this is rectifying the circuit. This is, you're still getting AC at this point that's before the bridge circuit. Remember I mentioned it's the AC input of this bridge that's hooked there is still AC. The DC output is coming out of here. So let's disconnect that for a second. All right, now, so let me see what else I wanted to mention to you. Okay, I want to just enlighten you of just a little bit more of how this coil works in this particular transformer, what's really going on, so in case you don't know. The coil makeup is essentially an iron core. You know, you're going to have an iron core. And you have primary winding. It's just wire that's wrapped around here, I don't know, maybe 1 or 200 times on one side. Now, you notice that this wire, this coil is on the side, has no attachment to this coil at all. This is one single, if you was to stretch this out, it'd be one wire. If you stretch this out, it'd be one wire. So they are not connected. This wire that's in this coil is not connected to this, or vice versa. This is a whole separate coil. And the way that it functions is using this iron core to more or less transmit the AC generated magnetism into the coil over here. It just all worked off of magnetism. So it's isolation. You can consider this like an isolation transformer, except for the fact that because the wires are not connected, so the circuitry behind it don't have to be connected as well. The primary can handle 120 volts AC, which is, like I said, it's a very high level and dangerous voltage. The AC is transformed and stepped down, actually, using a coil of certain windings to step it down to the voltage you like. This is a 12 volt output on this transformer here. So, like I say, it still remains AC, like that, just like in this side, it's AC. It's 12 volts, which is not enough to like cause you a lot of damage to you. However, it doesn't feel good to touch those ends. I've tried it, trust me, I know. So, I would never touch this. I've accidentally done that before, but not in this circuit, but I've done it, and I'm telling you, it is one type of experience you tend to never forget. So I use a lot of caution when I'm dealing with live line power. It's very dangerous. So anyway, this is just a little summary of how the transformer part of this works. And like I mentioned before, this is the transformer. When you buy them, they're rated. Let me make sure this is unplugged. Yes, it is. Okay. When you buy them, they're rated. They have the numbers right on top of there. They say like this one has 50. The input voltage is 110 to 120 at 50 or 60 hertz, and that's what I was telling you earlier about. So when you buy those, you can buy them like at 12 volt output AC, 6 volt output AC, 18 volt output AC. Most of your alarms, like you have in your home, will be an 18 volt AC output. If you was to take an alarm panel loose and look in there, you would see that it would be on the line of 18 volts instead of like this one is 12. Okay, so that's essentially what I wanted to demonstrate today, is how a simple diode like this, or devices like this can be used to make an unusable AC supply into a usable DC supply, which if you're going to use it for household goods, laptops, cameras, whatever that need DC, you can use a converter, which is simply a bridge, teamed up with a transformer, and then you can get AC output as we're showing you today. Well, I think that's really all I really want to talk about today. I hope this kind of clarified, you on how diodes work and some of the uses you can get from it. So I'm going to end this video because my camera is timing out. All right, thank you. Okay, my camera was timing out, so I had to hurry up and make this last little note before I go. I want to say I hope you guys enjoyed this presentation, and if you did, please give us a thumbs up, with a thumb, or click on like on the video, share it with friends, and comment. I really appreciate all your comments because I read them all. And if you have some advice or safety tips for me, let me know. I'll spread it around for you. But anyway, that's all I have for you today. Take care. Bye.